Welcome everybody to our second Focus on Geothermal webinar that we present in cooperation with Think Geoenergy. My name is Jochen Schneider and I'm the Director of Enerchange. Today we welcome Edda Aradóttir, the CEO of Carbfix. Shortly to the course of action, the webinar will be recorded and published next week on YouTube. Please contribute to the discussion via the chat and please follow us on LinkedIn and Twitter with likes and comments. And now we want to start, and I am glad to welcome Edda Aradóttir. She studied at the University of Iceland with her bachelor in chemical engineering in 2004, her master in theoretical chemistry in 2006, and the PhD in reservoir engineering in 2011 in collaboration with the Lawrence Berkeley National Laboratory. She was then starting at Reyjkavik Energy as the head of innovation and strategic planning, while also being the project manager for the Carbfix project. Last year, she became CEO of Carbfix, a company mitigating climate change by capturing CO2 and turning it into stone. Edda, we are looking forward to your presentation. The floor is yours.
Thank you, Jochen, and thanks for having me here in this webinar. Happy to be given this opportunity to share our Carbfix story with the geothermal community throughout the world. I think I'll just jump directly into my slide here. So as Jochen already mentioned in his introduction, Carbfix mitigates climate change by capturing and turning CO2 to stone underground. And this process actually happens in less than 2 years through proprietary technology that imitates and accelerates natural processes that are already happening in nature in specific rock formations. And our company's mission is to be a key instrument to tackle climate change and substantially reduce CO2 emissions. A bit more about who we are. Carbfix is a subsidiary of Reyjkavik Energy, the largest geothermal energy company in Iceland. And we were established, as Joachim mentioned, as a company last year. So we are just in the sort of first few months of operating, not just as a project and a research project, but also as a company. The current flagship project of Carbfix is operated at Hattisheidi Geothermal Power Plant. On Power, our sister company within the Reyjkavik Energy Group, operates the power plant, and you can see a picture of it here on the slide. Hattisheidi is the largest geothermal power plant in Iceland, with a current installed capacity of 300 megawatts electricity and about 200 megawatts thermal. We annually now capture and inject some 18,000 tons of CO2 and H2S from the power plant and inject it into nearby basalt formations, where natural reaction transforms both of these gases to minerals. Carbfix started out as a collaborative research project between industry and academia in Iceland, Europe, and the US in 2007. And so we've come a long way since then. And throughout this journey, we have received significant funding from the European Union, as well as national funding bodies, which of course we are very grateful for. Without it, we wouldn't be where we're at today. But in just 7 years, an outstanding team of scientists, engineers, and craftsmen transformed what was an idea on paper in 2007 to a proven industrial scale process in 2014. And this timeline here, showing the first few years of our journey, sort of indicates how we went about transforming an idea on paper to industrial scale operations and equipment. So in the first few years, we were in the preparation stage, doing lab experiments, modeling, field studies, design and construction of equipment, and of course acquiring the necessary permits and licenses to do the pilot phase, where we tested all of this out. And this was then in 2011 and 12 when we did the pilot injections. And early on we saw that the method was working as intended. We were seeing the type of reactions happening in the bedrock as we had anticipated, and so we decided to scale up to industrial scale, and we started the first phases of this then in 2014. So now we're at the point that we have a proven industrial scale methods for conditions that are similar to the ones we have at Hellisheiði. And this schematic just explains in a very simple way what the process entails. So previously we used to emit all the geothermal emissions just out of our cooling towers at the plant. But now what we do is that we take the mixture of the geothermal gases into a scrubbing tower, taking the gases in at the bottom, and then we have a shower of water coming in at the top. And CO2 and hydrogen sulfide both dissolve in water. It's basically the same process as happens if we make carbonated water or soda water at home. So this is what we get out of this scrubbing tower: water with dissolved CO2 and H2S, should it be available. And this is then the fluid that we inject into the subsurface. So we inject CO2 charged water into the basaltic rock formations located around the power plant, and their natural reactions take over, transforming the CO2 we inject into carbonate minerals. And this happens through chemical reactions, which happen in two stages. First, we actually dissolve the basaltic bedrock, releasing calcium, magnesium, and iron into the water phase, and then these meet up with the dissolved CO2 to form these carbonate minerals. And I'll come back to that a bit later. So in addition to this capture and injection from a power plant, we have also teamed up with a Swiss company called Climeworks, and they have developed a technology that captures CO2 from ambient air. So what we have also demonstrated and are continuously doing now since 2018 is that we take CO2 captured from air and add to this downgoing stream of water with dissolved CO2 from the power plant. And here we have a better explanation of the processes that happen underground after injection. We have the basalts and similar reactive rock formations that release calcium, magnesium, and iron into the injected water phase when it comes in contact with the bedrock as the fluid is acidic. And then automatically we have chemical reactions if conditions allow for it in the subsurface that transform the CO2 we captured and injected into these new carbonate minerals. And this is, in fact, nature's way of permanently storing carbon. And what we have then done since we started the Carbfix journey is that we figured out a way to speed up the process through science and innovation. This figure here shows how we have, since 2014, when we began capturing and injecting CO2 at the sort of industrial scale at our power plant, how we have scaled up since then. The first year we were capturing part of the gases coming from 2 of the turbines at the power plant. Then we doubled that capacity in 2016 and have been fine-tuning and optimizing the system since then. And last year a decision was made to continue increasing the capture and injection capacity. So currently we capture about 30% of the CO2 emissions from the power plant and about 75% of the H2S emissions. And last year a decision was made to become as close to zero emission as possible, and this is then a timeline that we are working on now. How soon can we reach that goal to be near zero emissions? And it is to be achieved both at Hellisheiði and Nesjavellir, the other large geothermal power plant we operated, no later than 2030 for both plants. Here I show you information about our on-site cost. Because of adding this Carbfix technology to the power plant, and the costs they are low compared to other similar carbon capture and storage methods and projects. The overall cost is just below $25 per ton over the lifetime of the operations, and this then includes both the OPEX and the CAPEX. And as you can see, it is the capture phase that dominates the overall cost. And if we compare this cost to the price of CO2 allowance, for example, in the European emission trading system, we see that last year we were lower than the price of emission allowances. Of course, during COVID, the price has gone down a bit, but still the method is competitive to the market price of allowances in Europe. And this fact has reached the ears of at least some of the companies that operate under the ETS system, and so we have begun dialogue with some of those to assess whether Carbfix might be an applicable method for them to reduce their emissions. If we look at the broader picture of climate change and the Paris Agreement, this figure here shows the cumulative emission reduction that we need to achieve by 2060 for us to reach our goals set forth in the Paris Agreement. And overall, we have to reduce emissions cumulatively by over 1,000 gigatons by 2060. And of course, that's a huge number, but we have to bear in mind that we are, of course, then looking at different solutions when it comes to moving, for example, to renewable power production as opposed to fossil fuel based. We need to increase the efficiency of our overall systems, switch fuels in the transport sector, etc. And then we also have a rather large block here labeled CCS, carbon capture and storage. And it is a fact that we will not reach our goals without widespread application of carbon capture and storage. So this is, of course, our task then in Carbfix, and of course others doing CCS throughout the world as well. So although Carbfix was developed in the geothermal sector, its applicability actually goes way beyond geothermal. And I mentioned this briefly earlier when discussing the European trading system with CO2 allowances, because actually the method, it doesn't care where the CO2 is coming from. As long as we have a source of CO2, favorable rock formations and water located in vicinity of each other, then the method is applicable. And it could be applied in the power sector, not just with respect to geothermal production, but also coal, natural gas, oil, biomass, and others. And when it comes to industrial production, the method is also applicable to steel production, cement, silicon, aluminum, and more. And since last year, Carbfix has been in collaboration with the power-intensive industry, as well as the Icelandic government here in Iceland, to jointly work on assessing whether Carbfix could be applied to reduce CO2 emissions from the power-intensive industry here, and this is then mainly aluminum and silicon production plants. So that's a very interesting project that we are working on. And then we are actively working on assessing the feasibility of applying Carbfix in other industrial sectors as well, and then not just in Iceland, but in other parts of the world. Here we have a map showing the sort of most favorable locations around the world suitable for mineral storage in the subsurface. And you can see that if we have a look at the purple and orange areas, these cover a significant part of the world, both on land and offshore. And if we combine all of the storage potential in these formations, the storage potential is orders of magnitude larger than what we would need from burning all fossil fuel on Earth. So if we put this into in perspective with the previous slide I showed earlier, indicating how many gigatons of CO2 we have to store underground by 2060, we will only need a very small fraction of the bedrock shown here on the map. And we also see that we have these formations located on all the continents, and as I said, also on the ocean floor. So our mission at Carbfix is to be a key instrument to tackle the climate crisis and substantially reduce CO2 emissions. And our scale-up concept consists of on-site carbon capture and mineral storage, where that is possible. And this then requires a source of CO2 to be located in vicinity of favorable rock formations, and also to have access to water. But in addition to that, where emissions happen a significant distance away from favorable storage formation, we foresee capturing, of course, on site, and then using various transport methods to get the captured CO2 to, for example, mineralization hubs, where geology is favorable and large quantities of CO2 could be stored. And if conditions allow for it, direct capture of CO2 from air could be implemented at some of these locations as well, if renewable energy is available. So if we are to reach our maximum impact with respect to reducing global CO2 emissions, we are, however, aware that we haven't finished fully developing the method. We can definitely still improve it and increase its applicability. So further research and innovation that we are and will continue working on involves, as I mentioned, focusing on other power and industry applications, and also consider different rock formations, not just basalts like we are doing now, but also other, perhaps somewhat less favorable rock formations, but that might still do the job. And this we are, for example, working on in a currently funded European Union project that is called GECO. It stands for Geothermal Emission Control. And there we are assessing the feasibility of applying Carbfix in other geologic formations, with plans on demonstrating injections in Turkey, Germany, and in Italy. And then, of course, we want to be able to use seawater. And then all of the basalts we saw were located on the ocean floor. And this is an ongoing research. We know that we can use seawater to dissolve CO2 in, so we don't need fresh water. We also know from lab experiments that the same mineralization reactions happen on the ocean floor. So this is a very important aspect for us to continue developing the technology, so that we will be able to apply it first near shore and then eventually offshore. And then, of course, we will continue assessing how capturing CO2 from ambient air and Carbfix can work with each other, these two technologies, to reduce the amount of CO2 already emitted to the atmosphere. So this concludes my presentation. If you want to get more information about what we are doing, please have a look at our website. It's www.carbfix.com, and we also try to be active on social media, Facebook, Twitter, and LinkedIn. So please follow us there as well. And thank you.
Okay, thank you very much, Edda, for this very interesting presentation. And we have already many questions for you, and I will start immediately with the first one. The Carbfix has obvious advantages compared to other CO2 storage projects in sedimentary systems. Has it been any interest from other countries to investigate the application of a similar Carbfix solution? For example, places where abundant basalt formations occur, such as volcanic islands in Madeira, Canary, Cape Verde, or Azores?
Yes, we've definitely received a lot of interest from different parts of the world. For those particular islands that you mentioned, yes, there has been some interest, but that is perhaps not the most active ongoing dialogue. But we would be, of course, very happy to assess the possibilities there. Of course, bearing in mind that in these islands we have very similar conditions as found here in Iceland. So we already have a pretty good understanding of how injections would work and how the mineralization reactions would occur. And there we would be expecting a similar rate as here in Iceland. So the 2-year then framework to transform the CO2 that we inject into minerals. So to sum up, yes, a lot of interest. but perhaps currently the most active interest is not necessarily from these islands that were mentioned.
Okay, thanks. Another question is, what would you consider to be the main challenges to the Carbfix applications? Is there any environmental risks that should be addressed?
Well, of course, there are always some environmental risks, and when it comes to injection, of course, we're all aware of the risk of induced seismicity. So we are very careful on how we go about our injections, and of course, we monitor it thoroughly. We haven't had induced seismic events because of Carbfix injections here in Iceland, but we have had induced seismicity just because of injection of wastewater from power plants, and this happened close to 10 years ago, and we learned a lot from that. So now we have a strict procedure on how we go about injections and modifying injection. So that is one of the risks. But then when it comes to other risks, we minimize those by exploring and researching potential injection sites very thoroughly before we do any injection, so that we're able to do the injection in such a way that the environment isn't negatively affected. And then, of course, it's important to keep in mind that these are natural reactions that are occurring, that are mineralizing the CO2. So we are simply using nature's way of getting rid of carbon.
Okay, thanks for this answer. There is another question. It's going in the same direction. Is there any risk of polluting aquifers with drinkable water while injecting CO2 diluted?
Yes, of course. If the injection isn't designed in such a way that such risks are avoided, of course such risks could be available. We always inject CO2 to great enough depth that this is not an issue, and then the injection wells are cased to a large enough depth that there is no risk of contaminating the groundwater systems closest to the surface. And then, of course, we do very extensive monitoring to confirm this. So we have, from the beginning, done countless samples of shallow and deeper wells in association with our injection, and we also do flux measurements on surface. And with this, we've been able to demonstrate that, at least here in our ongoing operation, there is no risk of contaminating the groundwaters.
Okay, thanks. Then there is a question about the mineralization. What about the injectivity in basaltic rocks? Are you injecting into tufic rocks? And the second question is about the volume of balance. If you have mineral growth in the subsurface, how much voids can you fill with how much injected CO2? And is there the danger that you close the voids and the injectivity might be reduced?
Yeah, so this was actually one of the risks that we were most afraid of before we started injection, because the intention is, of course, to gradually fill up the basalt with new minerals, and this could then lead to reduced injectivity of the injection wells. And but it turns out that this has not proven to be the case. We have not seen decline of injectivity in our wells, and the reason for that is that this mineralization reaction that transforms the CO2 into minerals, it happens in two stages. So first we are dissolving the bedrock, and this is what happens in the near vicinity of the injection wells. And the precipitation reactions then happen further away from the well. So at least in our ongoing injections, we have not seen decline in injectivity of wells. This could, of course, happen. This depends on the locations at each site, but then it's the matter of sort of optimizing the injection in such a way that we maximize the lifetime of each well. And then I also want to mention that the wells needed for this type of injection, they are much cheaper than, for example, geothermal production wells. These are completely different wells. They are shallower and thinner, so they are much less expensive and much cheaper than conventional geothermal wells. So it is also fine that one has to drill new injection wells every now and then, but we haven't had to do so yet. And I forgot the first question. You asked 2 questions.
Just what about the injectivity of basaltic rocks? Are you injecting into tufic rocks also? Tufitic rocks also?
Yeah, I don't understand that term, but we are injecting into basaltic rocks, and of course we aim for. We want to have a specific, reach a specific injectivity for our injection wells. So we locate them in such a way that we optimize the likelihood of having high enough injectivity to be able to inject a specific amount of CO2 per year, for example. And then the higher the permeability of the formations that we are drilling into, of course, the more likelihood of that happening.
But in general, basalt has it a good injectivity or a bad injectivity? And is it improved by bringing in the CO2?
Well, here in Iceland, basalts, they have high injectivity, and the younger the basalts, the higher it is, and the more pore space is available for CO2 to be stored in the rock. We cannot really, we do not have a concrete answer of how much it might improve. This very much depends on what type of formation you drill into. Is it fracture dominated, or is it, the flow matrix dominated? But what we can say for sure is that at least we do not have decline of injectivity in our current wells.
Thanks for your answer. A question about the origin of the water. You just mentioned you need fresh water for transporting the CO2 in the reservoir or in the basalt rocks. And where does it come from when you are in continental regions? There are often problems with freshwater supply.
Yes. Yes, we are aware of. We are very much aware of that, and know that this is certainly an issue in many regions throughout the world. In our current injection at our power plant, we actually dissolve the CO2 in condensate. So we condense the steam, and that's the water phase that we use for dissolving the CO2. So there the process is more or less a closed loop. We take up as a part of the power cycle of the power plant. We take up geothermal fluid, and then we redissolve the CO2 in the same fluid before it goes back into the ground. And this is the model that we work with. We take up from the injection formation. That's where we take the fluid from that we want to use for dissolving the CO2, and then we can recycle the fluid. So once the CO2 has been mineralized, we recycle the fluid again. And this is what we foresee doing. Of course, if and when we move to the shore and use seawater, there we have endless amounts of water. So there we do not need to rely on such a circulation. but then we would just use the seawater to dissolve the CO2 and put it into the sub ocean or subshore floor.
So are there special requirements for the water?
No, not really.
No.
Of course, the temperature of the water affects how much CO2 can be dissolved per liter, etc. So we do not want to have it too hot. We work with about 20 degrees, if I remember correctly. But no, not necessarily any specific requirements for the water.
Okay, thanks. There is another question. Would your concept also work in limestone deposits as storage formation?
Now I'm not a geologist, so what I do know is that limestone is not the optimal storage formation. We wouldn't have the same type of mineralization happening there. However, the process and the technology could be applied in different formations, and it could be applied in saline formation, for example. But we wouldn't see the same amount of transition to minerals. So there we would basically just be storing the CO2 then dissolved in water. But there are specific rock types, and then we move into the basalts and rock types that are similar to that have high amounts of calcium, magnesium, and iron, and these then would result in the largest transformation and the most rapid transformation of CO2 to minerals.
Okay, thanks. There is another question about basalts commonly exhibit mineralization with their vesicles already. How difficult do you anticipate finding enough suitable rock formations for storage with enough capacity to meet the requirements?
I don't think finding the rock formation will be the sort of limiting factor. We know the formations are there. The limiting factors and the bottlenecks would probably more be oriented in sort of getting the funding required to invest in infrastructure that is able to capture and inject the amounts of CO2 that we need to inject. And also on top of that, there are still, unfortunately, at least in some parts of the world, sort of regulatory barriers. So I would think that these would be a greater barrier in achieving the goals we need to achieve rather than the storage formations per se.
Okay, thanks. Then there is a question about the casing and the cementation of the casing. Within this regard, also the question about the pH value of the reinjected fluid, may it affect the steel casing? Is in the end one part of the question. The other part is, does cement holding casing in place come in contact with the injected CO2 and H2S? If so, have you checked on the integrity of these materials? And then thanks in advance for the answer and for the very interesting presentation.
So with respect to this, we do the pH of the fluid we inject is around 4. So if it were to come in contact with black steel, it would corrode. So all our transport pipelines, etc., everything that comes in contact with the acidic fluid containing the dissolved gases, that is rust-free steel. But we do the injection, of course. Our wells that we are using pre-existing wells at our power plant, for example, that have just the black steel casing. So to protect the casing, we have an inner pipe made up of a different material that we inject the water with the dissolved gases into, and then we also co-inject into the same well just normal separated water from the power plant. By doing it this way, we make sure that the carbonated water does not come in contact with casings that might corrode. With respect to the cementing of the well, unfortunately, I can't comment on it, but I just don't know the answer to that. But how the cementing was done, etc. But I would just encourage the person that asked the question to contact us via our website, and we can then certainly find the right person to provide more information about the cementing.
Okay, thanks. Well, there are a lot of questions about the permeability and if there are in the end changes in the permeability by injecting CO2 and if the rocks are affected. And then there is also a question if oil and gas companies are aware of Carbfix.
Yes, at least a few of them are. Yeah, I believe they are aware of us, but there are still no projects planned with respect to oil projects, for example. We are more focused on sort of trying to figure out how we can reduce emissions from industrial production that we will still need to rely on in the future, even though we have sort of moved towards renewable energy in the power sector, and that's where the steel and cement and the metals industry, for example, comes into play. So we're more focusing on those operations and productions rather than oil or power plants that burn fossil fuel.
Okay, thanks. Then there is a question, what type of continuous monitoring do you have in place?
So for continuous monitoring, we have seismic monitoring. We mainly do still monitoring in such a way that we have to go to the site and acquire samples from monitoring wells. So our main monitoring involves using tracers to label what we inject, and these are then different types of tracers: reactive tracers or gas tracers or just conservative tracers that dilute. And our main monitoring involves following how these show up in the monitoring wells, and then also just then following the chemical signals in the fluid phase. So this is we mainly do monitoring through these types of methods. So that is of course not continuous, but we have to go on site to do it, but we do it continuously. Or you know, with specific periods in specific time periods. But then we also regularly do surface gas flux measurements, and I'm sure I am forgetting some of the aspects. But at our website, we actually have a very detailed list of all the scientific publications that we've put out throughout the years, and these provide the very detailed information about the monitoring campaigns we do. So I would also just encourage those interested to have a look there.
Then there are thanks for the initiative and excellent presentation and clarifications during the discussion. There is another question. If there is no decline of injection, how do you make sure that there is no escape of the injected fluid?
Yeah, so that was basically through the monitoring that I was describing earlier. So we do very extensive monitoring. So we have a lot of data that confirms that we do not have leaks and that we have the mineralization going on according to the reactions that I showed. So yeah, it's basically the same answer. And on top of that, in the scientific papers that we have on our website, we also have a lot of the data. They contain a lot of the data that we have acquired through the monitoring.
Then again, thanks for the great presentation. Could you please tell me if the injection is continuous or if there are periods of shut-in the injection well? Did you have any situation where the shut-in happened, and did it cause any problems in operational point of view?
Yeah, the injection is continuous. Of course, we might have to turn it off if there is plant maintenance, for example. So it is continuous apart from that. But we do not just have one well equipped with infrastructure to carry out the gas injection. We have two at the power plant, and both can accept all the gas. So if there is something going on, measurements or maintenance in one of the wells, we just switch the injection to the other one. But of course, particularly when we were still in the pilot phase and the sort of commissioning phase of the injection, of course, there are always some issues that come up, but we have overcome all of those. So more or less, it's just an automatic, smooth injection and continuous.
Okay, thanks. Another question: the pH of the water does not control the dissolution of basalts? Question mark. By using condensate in Helice, the pH is rather low compared to normal fresh or seawater. Would not this affect the deposition rate?
Yes, but then we would just we want to have the pH of the fluid we inject low enough that we have dissolution. So this would then be the matter of sort of doing the dissolution in such a way that we still have low enough pH. So that is an engineering aspect.
The next question is: what is the expected quantity and frequency of drilling disposal wells? So do you expect more wells to be drilled?
So at the power plant, we do not foresee drilling new wells. We already have a lot of injection wells for the injection of water. So we would simply equip these wells with gas injection capacity if and when, for example, when we scale up. We have been operating the current injection wells for over 6 years now, and as I said, they haven't declined. Of course, probably eventually we will have to drill some wells or add on other existing wells, but according to everything that we know, based on what we have done until now, this is not something that would happen regularly. So perhaps every 10 years or so, but this is then something we are also learning. Yeah.
Yeah. Okay, thanks. One of the last questions: how much time takes the mineralization process?
Yes, so this at Helice it takes 2 years, and then we have mineralized more or less all the injected CO2. This could, of course, be different between locations because the mineralization rates, they are dependent on different factors, the surface area of the rock that we are injecting into, the temperature of the formation, the pressure. So there are different factors that come into play, but in our current injections, this is happening in less than 2 years. just to add, and this is then a completely different timescale than in the classical supercritical storage of CO2. There, the transformation to minerals happens in thousands to hundreds of thousands of years, if it happens at all. But then, of course, we are dealing with a completely different geology.
Thanks a lot. Here is one last comment. Really great presentation, and I appreciate a lot the honesty. Also from our side, thank you very much for this very interesting presentation and these lots of answers to the many questions at the end. And we wish you all the best for the upcoming things you're planning and learning a lot for the future. I hope everything goes well, and I want to conclude with the next event. It's in 1 week. It's again in German, and it's about the Genesis well in Hanover and the prospection there of the sandstone horizons. The next focus on geothermal will be in 2 weeks, and we will inform you in the next week what will happen. So thanks again to Edda and to you all listening to the webinar. Have a nice weekend and hope to see you soon.
Thank you.